Hi everyone, I'm Bramsh Chandio. I'm a PhD candidate in the Department of Intelligent System Engineering at Indiana University. And today I'll be talking about bundle analytics. We recently published this paper in Nature Scientific Reports. It's a computational framework for investigating the shapes and profiles of brain pathways across population. The main idea behind bundle analytics is to provide users one platform where they can perform group differences in white matter tracks at specific locations. So user can go from whole brain tractogram to bundle extraction and then creating the bundle profiles, performing statistical analysis on the bundle profiles. And we also provide a new tool for shape analysis of the bundles, which can also be used as quality assurance. And this whole framework is available in DIPY. So in this paper, we worked on Parkinson's disease data to find differences at specific locations along the length of the track. Like in the C, we can see the specific region is highlighted in red and yellow. But it is a generic framework that could be used to study any neurological conditions, effects of medication for the longitudinal studies to see post-surgical validation, comparison between any kind of two groups, like groups to find the group differences in between two genders or effects of age, or just to study brain pathways. So when we have, we start from the input tractogram, and we get these tractograms from the tracking algorithms, and the output is this whole brain tractogram. But this is a complex data where the streamlines are unordered and unstructured. As we can see here, some streamlines start at this point, and then some are starting later, some end earlier. And we don't know in the tractogram from where it is starting, if the first point is starting from here, ending here, or if the first point is starting from here and ending here. And it's densely populated, so it's difficult to inspect it visually or computationally, like inspecting each streamline. And there are also many false positives. So that's why we extract specific bundles, because the specific bundles have a specific function associated with them. So it's better to look at those white matter tracks, which are similar in the shape and have same function. So for the bundle extraction, our approach starts by having a whole brain tractogram shown in A, and we need a model bundle tractogram. We want to register all of our input data into a common space. So here we provide a model atlas, which is in MNI space, and we also provide bundles with it, 30 bundles. So we first start with streamline-based linear registration to register input target tractogram into model bundle space. And we have it in the C step. After that, we perform bundle extraction. So in this paper, we introduced another step in RICO bundles method, which we call auto-calibrated RICO bundles. So first we start with providing a model bundle and registered atlas in common space. So now they both are in the same space, in this case MNI. And we perform RICO bundles to extract the initial bundle from the input data. And what we do next is, in the next step, we provide this extracted bundle as a model bundle to RICO bundle, and we call it refinement step. So this time our model bundle is not coming from an atlas, but coming from data itself, because this is already part of the data. We don't even need to register it. And in this case, we reach more streamlines, or we have better extraction, which has influence from data itself. So we extract 30 bundles for, in this paper we did for 64 subjects. So after we have extracted bundles, if we want to do group analysis on the whole bundles, it is kind of difficult to do that, or maybe not a good idea, because bundles vary a lot in the shape. If we see at the endpoints, there's a lot of fanning, and in the middle it's more similar. And also if we project some measures, like here we have projected fractional anisotropy over the bundle, arcade fasciculus. And we can see at the end points, it has lower FA. Here we can see towards green it's 0 and towards red it's 1. And in the middle part, it is around 0.5. And then here it gets 0.7. So the values differ along the length of the track. So it's better to look at specific region, which is similar in shape and also in the measures like FAMD, RD. To do so, we have this step in BUAN we call bundle assignment map, where we create smaller segments on the bundle. So we start with input bundle A, and then we have a model centroid, which we have from the model bundle that we use to extract bundles. And we project this centroid over the input data in the B. And each centroid is shown in a random color. So different color shows different centroid. And then we create these segments. In this case, we are creating 100 segments. So how do we do that? We can look at this one here. So let's say this is our input data where we have these streamlines, 7 streamlines from a bundle. And then this yellow one is the model bundle centroid, which was, in this case, it was this one. And then in this case, we have 5 centroids on the model bundle. And what we do is we take each point from each streamline and calculate distance, Euclidean distance from that point with all the model bundle centroids. So in this case, if it is closer to this centroid, it will have a minimum distance between these 2 points. We assign that point to this centroid, or we just give it a label, segment number. So this is centroid 1, so we give it a label 1, this point, and then move on to the next point. And we calculate the distance between this point and all the centroids. And in this case, it is near second centroid, and we assign this label second segment. In this case, we do this with all the streamlines and all the points on the streamlines. So here we can see how the representation looks like. So we are keeping the data as it is. We are not changing the format of the data or simplifying the data or discretizing the points on the streamlines. We keep whole information as it is. We just assign it to some segment number. So here are the segments that how we have created, like divided it into segments. And this is how it looks like in the C part, where we have different colors for different segments. Now, if we look at these segments, they are very similar in shape, and location is also same. So it will be, we will analyze these specific locations to find group differences. And this is also helpful because when we look at some streamlines, such as this streamline number 5, whose first point starts here, but we are not assigning it to first segment because this is far from the first segment. So we assign this to segment 2. And then same for the streamline number 7, it's ending earlier than other streamlines, but we don't say that this is part of 5th segment. It's part of the 4th segment where it belongs. And this is another example on a different track. So this is a parameter that the user can select how many segments they want to create. So by default, it's 100. In here, it's 40. And if a user doesn't want any segments, they can just say 1 segment, and it will be the whole bundle. So for the bundle profile analysis, what we do is we have all the subjects. So in the red, we have patients. In the green, we have controls. And we have these segments created on the bundles. So for each segment, we will project some measures on it. So it could be DDI measures, FAMD, RD, or other measures like GFA or QA. So per segment, we take the data from all the subjects and run linear mixed models per subject to find the group differences on that specific segment. And this is how the result plot looks like. So in this case, It's for arcade fasciculus in this example. And we can see this area where we have the significant group differences. And then we can go back and visualize on our model bundle that where is that segment. So we can have at different segments for different measures, we can have group differences. Like here we have for MD and AD in the red and FA and GFA in yellow. So we apply linear mixed models for the group analysis. Linear mixed models are extension of simple regression models where we have in simple regression models, we just have fixed terms, but in linear mixed model, we have this random effect term as well. So in our case, the fixed effect term is accounted for the population mean, and the random effect coefficient accounts for the specific deviation from population mean. And this is the error term. And in our case, the response could be the anatomical measures such as MD, FA, RD. And why we include random effects is because random effect models are used to properly account for the correlation between points on the same streamlines belonging to one subject for a specific subject. Because as we saw, from one streamline, we can have multiple points belonging to one segment and also multiple streamlines from subjects. So that is accounted by this term. So in our paper, we studied Parkinson's data. We selected a specific subjects in a specific age group, that is 59 to 61. And then from that age group, we selected two groups, Parkinson's group and control group. In each group, we have 32 subjects, 14 female and 18 male in both subjects. So we kept the same ratio of male to female, and also a specific age range because we didn't want to have artifacts in their analysis due to the age differences or gender differences. So here we have the output plots for functional anisotropy. So in these plots, we have plotted, in most of the plots, we have a left and right bundle in different colors, except some like here, this is in the pink, we have CC mid. And in the last, we have just V. So here we can see the upper line is for p-value less than 0.001, and the lower horizontal line is for p-value less than 0.01. And along the x-axis, we have segment number. On the y-axis, we have minus log p-value. So we say wherever we see the higher significant group differences, which are highlighted within this region of these two lines. So in linear mixed models, the assumption that we have is that there are no group differences. The mean between two populations is same, but we reject that assumption when we have higher p-value, which is in this case less than 0.001 or less than 0.001. So we see in FPT right, we see a group difference here in between 20 to 40 segment. And in FOF, both left and right, we see around 60. And to see what specific difference there is, because this is just telling us that we have some group difference, but what is the group difference? So here we have projected the mean FA for control and group for the bundles. So in the red we have for patient, in the green we have for control. So we can see where in the arcade fasciculus we see around 70 higher group difference, and we can see there is a difference between their mean values where patient FA and the patient increases as compared to control. And in FOF around 60, again, we see that. So in most of the plots for the FA, we see FA increases in patients and as compared to controls. And here in the second row, we have for MD. So because MD values are very small, that's why sometimes we see a spike, like in this FOF right, we see a spike around 90. This is because if there is a one outlier subject which has a higher value of MD, when we take the mean value average, we see this spike. But linear mixed model is not giving this area any significant group difference. As we can say, the p-value is very small. It's not like significant in this region. So we also proved that we are not, our analysis is not affected by outliers. And in most of the MD plots, mean MD in patients decreases as compared to controls. So to sum it up, first we create these segments on the bundles, and then we analyze each segment from all the subjects. So for all the subjects, we have same model bundle, so we know that each segment is same, the index is same for this in each subject, and it belongs to same location for all the subjects. And we take and analyze per segment with linear mixed models. From there we find the group differences areas, and from there we can go back and project this specifically where on the bundle we have that region. And to see what are the differences, in the D plot, we have the histogram plot where we have count on y-axis, and on the x-axis we have the values. So this is like mean value per subject in that, only in that segment. So here we have selected these segments, 58 to 62. And what is the mean value per subject on that? So in the red, we have patient, in the green, we have control. So we see that for FA, it increases for patient FA, and MD decreases for patients. And it's the same case for both if of left and right. So this was the bundle profile analysis part of the paper. And then we have shape analysis part of the paper, in which we perform shape analysis with bundle adjacency method. So if we have two given bundles, B1 and B2. So we say that there is at least one streamline in B1, which is adjacent to B2 if the distance between two streamlines is less than some threshold, MDF distance. So we say the coverage of B1 by B2 as the fraction of B1 that is adjacent to B2. Coverage will range from 0 when all the streamlines in B1 are too far from B2, or 1 when every streamline in B1 is adjacent to B2. So we calculate bundle adjacency, or as we call BA, as the average of coverage of B2 by B1 and the coverage of B1 by B2. Here. So to explain it further, we have created this figure where we say that we have a parent bundle P, and then we create some 5 child bundles from this bundle itself. So the C1 is a replica of P. So it is the same bundle. And the C2 is some part of P, and then we keep removing some parts from the bundle to create C3, C4, and C5. So in C5, we just have the middle part of the bundle. So how we can use this to find shape similarity? This method depends a lot on the threshold, what threshold you give it. So if we give it a lower threshold, it will be very strict in giving the shape similarity score. So on the left, we have in the black threshold 5, and on the right, we have threshold 15, which is higher threshold, more lenient. So in the first case, since it is a replica, it should always give you 1. And we assume that they are in the same space, of course. And then in the C2, we see that if it's lower threshold, it's giving it 0.82. So 1 means that it is high shape similarity, and 0 means no shape similarity. And when we have higher threshold value, it gives it 1, although there is some part missing. So it depends on user how much they want the method to be strict. If they want it roughly to be same, they can give it a higher threshold, or if they want exactly to be same, then they can give it less threshold. And as we move towards right, we can see in the end C5, because it's just the middle part. So threshold 5 gives it 0, that it's not the same shape. But if we give it higher threshold, it gives a 0.5 because it is part of this bundle. There is some shape that is similar to this shape. So this could be used as a network graph where we have on the left connected, fully connected graph for the shape similarity among 5 bundles. where each bundle is connected with every other bundle. And on the edges, we have this shape similarity score. We can also write it as a matrix, similarity matrix, where in the diagonal, it has shape similarity calculated with itself. So with itself, it should be 1, and with all other bundles. So wherever we have darker, it means higher shape similarity. And when our color is diverging towards white, there is less similarity. And the threshold used for this was 5. This could also be used as quality assurance. So wherever we see there is more white lines or lower shape similarity, we can say that those subjects are outlier subjects, or they are not very good subjects. There was some problem with bundle extraction or tractography method or registration. So in this, so what we do is same as before. We give all the patient data and control data, but this time we don't give it the segments. We give whole bundle as it is, and then we create this shape similarity plot for 64 subjects in this case. So first 32 belong to control, and last 32 are from patients. And then each pixel here, each point is shape similarity among two, calculated among two bundles. And like in this case, it's these two bundles. So for example, here we can say there is this one subject, which is like 39 subject, which has lower shape similarity among all of the other subjects bundles. So could be that there is some problem with it, or it's just like not so dense as compared to others. So we calculated this for 30 bundles. So in this, these are all 30 bundles. And we can see for arcuate fasciculus right, in most cases, we see that we are not finding a lot of bundles for this. So we have this white lines there, but most of them are doing well. And we have very strict threshold that we have used, that is threshold of 5. So this could be used for quality assurance. We can say that this bundle is not doing very good, this subject, and we can exclude that subject from our analysis. Here we are doing some clustering on it to find the groups between the groups. So to see which groups have similar shape in the bundles. So here we can see on the right, there are some that are more light in color, white. So we can say they have similar shape. And then we have this cluster, which is darker. And then these are like mixed. And here we also have green for control and red for patient to see what these subjects belong to which group. So this method could be used for multiple things. If we have a registration framework, we can calculate this before and after to see how well a registration has performed, or how well a bundle extraction has performed, to compare the extracted bundle with the model bundle. So in the paper, we performed comparison with automated fiber quantification AFQ. And this is so AFQ creates bundle profiles per subject. Per subject, we get one bundle profile, and we can analyze those or perform any statistical analysis over those on our. So here I'm just comparing the bundle profile creation part of it. So if we have input bundle like this, in the AFQ, what AFQ will do is it will discretize each streamline to have 5 points in this case. So each streamline will have 5 points, and then every point, like if we are looking at the first point, we take first point from all the streamlines and get the weighted mean of those to create the final point for the final mean bundle profile. So for the second, all the second points on the streamlines will be averaged to create the second point. And this way we'll create the 5 points, and we will have mean streamline, weighted mean streamline. And in the BUAN, what we do is we do not discretize it, but we just assign each point to the closest centroid. And in this way, we create these segments So we keep all the points on the streamlines, and we don't create a final mean streamline. We keep all the streamlines and all the points and use all of them in the analysis, and we just give them segment number. So this approach, BUAN approach, is better in a way because when we have this streamlined data, as I talked before, that it is kind of unstructured and we don't know where it is starting from. So if we give this point, which is the fifth streamline, if we give it the first point, in this case it's the first point, and then we average it with all other points, which are not in the same area, so the mean is not, like, it's not, maybe not ideal to take the mean of these, which are further from each other. But in this case, we'll take the mean of just this segment, and this will be in the second segment. So the output of this is all of the streamlines are saved in HDF5 file, where we have point and which streamline it belongs to, which group it belongs to, which subject it belongs to, and we also save the measures on it like FAMD. And here we can save this as one streamline with values of FA on it along the length of the track. So for the comparison, I ran this on 10 subjects, on just the arcade fasciculars of the 10 subjects, just the bundle profile creation part of it. So for the BUAN, it took 49 seconds, and for AFQ, it took 254 seconds. BUAN has multiple, it could be used in multiple domains of science, engineering, and medicine. Like a psychologist who wants to develop a theory about the brain, they can use it. A neurologist who wants to find which pathways of the patients have defects or deviate from normal population, or a neurosurgeon who wants to see the longitudinal effects of a patient after tumor surgery. An engineer who is developing new machine learning algorithms, they can use it. A data scientist could use it to find patterns in the data and extend the approach. Network scientists can use it to understand the connectivity of brain. A medical student who wants to learn the major pathways of the brain or investigate the possibility of new pathways. Or we can use it to quality control the data. And we can also adopt the same method as it is on the animal data. All we need to do is provide a population-based animal atlas for this case, and this whole pipeline should work. For the future, we want to try it on different data sets, like Alzheimer's data set, and maybe include more statistical methods in the pipeline. So I want to give a quick demo of it. We have this in DIPY. So all we need is 3 command lines to run this analysis. So with this paper, we have also provided the data derivatives. There is this data derivative for the 64 subjects where we have extracted bundles and the anatomical measures. And then we have this test subject as well, where we just have 10 subjects. So I'll use this one. So the first thing we need is an atlas, which we also provide here, and can be downloaded from here, which has whole brain atlas and 30 bundles in the MNI space. And another thing that we need is, as I showed this, the data set, which has some bundles. Oh, okay. Sorry about that. Which is the test set. So we can have, so I have bundles, which has bundles in it. So for this tutorial, I'll be just using one bundle, arcade fasciculars, but user can have as many as they want. And in the subject small, or the name could be anyone. I've just created subject small. So this has 10 subjects, 5 patient and 5 control. And in each subject, we have anatomical measures folder where we can have any kind of measures like DTI measures or GFA or any other measures. User can provide those. And then we have this original bundles in original space, in the native space of subjects, native space. And then we have rec bundles, which are in the common space. So this tool needs our input folder to be in a specific structure, which is the subjects, but the name could be different. And then we have control, and inside the control we have subjects. So each subject should have these 3 folders. Inside the folders, name could be different, and how many the files we provide them, that could be different. And then we have patient, and again for the patient we have same structure. And this is also explained here. So the first thing that we need to do is just first create a folder that's called bundle profiles. And so now I'll be running bundle profile part of it, where we just create those segments and save the information in HTF5 file along with the measures. In this case, we are just running on FA. So the command for that is DIPY BUAN profiles. And then this needs, first argument that it needs is a input folder or the path to the folder where we have the bundles. And then the second one is the subjects folder path. These are the 2 arguments it needs, but I'll just give it where I want to save my output. By default, it will save in where you are calling this from. So this will take around 1 minute, and it's showing what it is doing. So it's running on AF. And in the output, we will have HTF5 file for AF, FA. And we will use this output for a linear mixed model workflow. That workflow will need just the bundle profiles where we have saved these bundle profiles and the output folder. So this one just needs 1 argument. And it will save files, which would be p-values file saved as numpy, and also a plot value saved for each bundle. We also have this tool where we can visualize exactly which location we see the differences. For in this case, we can just provide p-value file and at how much significance we want, like at what level, the value of p-value where we want to see the significance. So this is now done. This time is per subject. So overall, it takes like less than a minute. So we can do to see what it saves. So this is just H5 file. And now for performing linear mixed models on this, I can create an output folder. And then I will run DIPY BUAN LMM command, which command just needs, is this one, just needs the folder with H5 files. And I give it the name of output directory. So what this command does is it takes segment. So for example, we have 100 segments. We take one segment from all the subjects and analyze one segment at a time. So it will run linear mixed models on one segment. Here it's showing that it's running on this number one, this number two. So it will run linear mixed models. If we have 100 segments, one for 100 segments. So the output would be p-value per segment, as we can see here. And it will save numpy file for p-values, 100 p-values, and also minus log p-values, so that if user want to visualize them, do something with them. And it also saves this plot per bundle, where it shows this is a region where we can see the higher group differences. This will take around 2 minutes to run for 10 subjects in one bundle. Just going back to the tutorial because it's done. So we have this, and now if I have this, so this has created one plot, and then it has saved the p-values. So if I look at the plot, it is this plot where we can see that there is some area around 58, which is less than p-value less than 0.01. And then we can now visualize it on the bundle as well, like this. So let me just copy this so it's faster. So here we use DIPY horizon, and we give it the model bundle and the p-value that we got from a linear mixed model workflow. And then we give it just the flag for BUAN and at what threshold for the p-value. In this case, I'm writing 0.05. So here we have all the regions where we had p-value less than 0.05. So this was 0.05. In the plot I showed was 0.01. So that would be different if I use that. And if I do that, I can write this. And I can also change the color of this highlighted area. You can just give it a color, RGB values for that. So now here it is showing me just those locations with p-value less than 0.01. In the start, we have some here. And then we have some here, here. And the last one would, yeah, here I'm just visualizing it with different color. You can provide the BUAN highlight with different value of color. And the last workflow is for creating this shape similarity profiles. So here this should be fast. I'm just creating the output folder. And then for this one, we can run DIPY BUAN shapes and give it the folder where we have our bundles. So this will find shape similarity in common space. And this is, so this one will save plot like this, and it will also save the values. So it will be a NumPy file with a matrix where we have the values of shape similarity score, which then user can use to do any clustering, to apply any clustering algorithm or do further analysis on it. So in case if you have any more questions while it's running.
Yeah, we are close to the end of the meeting. So normally we finish at 1. So we have 8 minutes. if you have any quick question for closing this meeting.
Hi, thanks for a great talk and a actually pretty interesting paper. I just started using the tool just the other day, and I was curious, is there a good place to ask or questions? I heard a distribution list. I was just curious, you know, that information.
Yeah, I'm putting this information in the chat. There is the DIPY chat room, it's exactly on the DIPY website. And there is a DIPY mailing list, so I'm gonna add that.
Great, that would be really helpful, thank you. I also wanted just a point of clarification. You were talking about the auto-calibration component.
Mm-hmm.
So you do the SLR, and then you end up with an extracted bundle, and then you take that bundle again, and you feed it back through Rico. Am I understanding that correctly? To do the refinement?
Mm-hmm. Yeah, so in kind of we are running Rico bundle 2 times, but the second time the model bundle is different. Model bundle is part of the input data itself. And then we prune some streamlines that are like further from the central stuff. And then we get this F top, which is smooth and clean.
The auto-calibration helps a lot to deal with small bundles, improves accuracy quite a bit
So
in
there were
segmenting.
like Unsynth, it was difficult to find it, but with this step we can find hard to find small bundles.
And it also allows to find the bundles without needing to play with any thresholds, especially for human adult brains. You will not need to play with any of the thresholds that the extraction tool Rico bundles has. So you just run it with input data and you should get bundles out if they, of course, exist in your data. If in the tractography you have bundles that are as appearing on the atlas, then you will find these bundles. Now, if you have animal data, then you have to take one or a few of the data and extract bundles on your own, because we do not provide right now an atlas for, let's say, mouse brains or kid brains. We only provide an atlas of bundles for adult humans.
So this is the output. This is plot, and also these values are saved in NumPy file. These are ones to perform analysis in it. So here we can see in the diagonal because it itself, so we have that one, and then for this one we are using the threshold 6 here, which is the default threshold, and which is kind of a strict, and we see that we have very good extraction and shape similarity among all the bundles. So if you want to use different threshold, you can just see BUAN workflow and then -h to see for -h for the help to see what are the parameters or if you want to change them, what the default one should work. And here there is this threshold if you want to change it higher or lower. And yeah, all of the other as well. Profiles -h. So in the profile we created 100 segments. If you want to create less or more, you can provide that in the number of disks. So you can provide how many disks you want. So if you are changing the number of disks there, you have to then change the linear mix model as well. So that is also just one. number of this parameter. Again, you can give it the one that we are using.
So more tutorial will come with this bundle analytics frameworks. Thank you all for coming for this talk. Thank you, Bramsh, for presenting. If you have any question, don't hesitate to contact Bramsh or to post them on like LFSA on the mailing list or on the chat room.